Okay, perfect. So this is what we started in the last class, bipolar junction transistors. That's a dual to MOSFETs. Okay, we looked at MOSFETs in the previous week. This class, this week, last class, we talked about bipolar junction transistors. The main difference between MOSFETs and BJTs is that one is a current controlled current source. Therefore, you see the current gain factor beta. Okay, the other MOSFETs is a voltage controlled current source. So you see the trans conductance GM. Okay, so I'm going to reinforce this idea a little bit more. Okay, the underlying architecture is the interplay between two diodes. There are two diodes. There's a base emitter junction. See, there's a base emitter junction and the collector base junction. Okay, fundamentally, the NPN or PNP BJT transistor, bipolar junction transistor, is a sandwich of p-type region between two n-types, or the other way around, okay? A sandwich of n-type between two p-types, okay? So by that token of argument, there are two diodes, and BJT is all about controlling the interplay of these diodes. How these diodes, when there are two diodes, diode 1, which is the emitter base junction, and diode 2, collector base junction, how each of these are biased. If both of them are reverse biased, then my MOSFET is, BJT is cut off. If one is forward biased and the other is reverse biased, then we are in the active region, so on and so forth. So corresponding to the four permutations that are possible, we can have different regions of operation, okay? So we are in cutoff, we are in active. When both of them are forward biased, we have saturation. When one is reverse biased and CBJ is forward biased, we have a reverse active region. Okay, we talked about this. And in addition, I mentioned the symbol. I talked about the symbol of BJT in NPN. Okay, with the arrow not pointing in, not pointing in. So not pointing in. That is NPN. Okay, and I mentioned that for NPN, we like to draw the collector up on the north, in between the base, and at the bottom south is emitter. Okay, and typically in the active region, this corresponds to the base emitter junction being forward biased, while the collector base junction being reverse biased. Okay, we looked at the regions of operation and then the corresponding PNP transistor for which VEB should be positive. Okay, and then I mentioned the emitter current is the sum, a big chunk of that is actually collector current, and a small teeny tiny amount is going into the base. Okay, now the relationship between IC and IB is given by beta. Okay, that's the current gain in active region. How much input current is going into the base, and as a result, what is the resultant collector current? Okay, so that's how well input current is converted into an output current. Okay, that's where we get an amplification. Okay, that's the idea. A small change in the input current, if that leads to a large change in the output current, then we have a really big current gain. Okay, and then we talked about the minority charge concentration. Now, in the forward bias region, we mentioned about all of this. Then I talked about similarities between MOSFETs and BJTs. Okay, and then the current gain factor, beta, is in BJTs. Fundamentally, BJTs are current amplifiers, you can convert them to voltage amplifiers by passing the resultant output current IC through a resistance. And we'll see that in this week's class. Okay. MOSFETs, on the other hand, are transconductance devices. The input that you apply between the gate and source, that translates into a drain current. That's the transconductance idea. Okay. So one is a voltage controlled current source, the other is a current controlled current source. Okay. Then we looked at the equation for current in forward active region. Okay. IC is IS times exponential of VB to VT. Okay. So if you think about it, let's see, can I draw a parallel between IC in BJT and ID in MOSFET? Okay, if you remember, ID had a squared dependence on VGS minus V threshold, which is the input. IC here has an exponential dependence on VBE, or the input base voltage. Okay, so the gain is typically larger. The current gain is typically larger in BJTs compared to beta. Okay, compared to G sub M. Okay, that's owing to the fact that the relationship here is exponential. Okay, the output current has an exponential dependence on the voltage. Okay, so that's the idea. And we can talk about that in the example today. But typically what happens is when people move from BJTs to MOSFETs in terms of technology usage, not all the designers were extremely happy with the lower gain values, lower GM, a transconductance, the underlying intrinsic gain values are lower for MOSFET compared to BJTs. Okay. All right, so that's what we did in the last class. So what we typically do is we use this equation, IC is IS times exponential VBE over V threshold, V thermal voltage, VT, okay? Now, we use this equation when we have a value for VBE. Once we have a value for VBE, the rest is all known. We should be able to estimate a value for IC. Okay. Once we have IC, finding IB is simply using the value of beta. Okay. Once we have beta, we use that. Once we have IC, we can also find IE. Okay. All right. We looked at the large signal model. This represents the forward biased VBE, and this should have a voltage of 0.7. Okay, that would be an approximation fair enough, close enough for small signal analysis. Okay, if there are places where we need to alter that assumption of 0.7 volts, I'm going to point that out to you. Okay, so corresponding to this VBE, once we have a VBE, I should be able to find IC over here. Okay, so that's the idea of so the DC voltage across this diode is 0.7, but then there's a small signal VBE as well. Okay, there's a small signal VBE that's changing around the base emitter terminals. Okay, all right, so we apply the generic procedure to start looking at some problems. Okay, the general procedure to solve some problems. Okay, let's start here. Let's start by the example problem by looking at the example problem where IS is given. Okay, IS is given to be some value. Okay, and beta is also given. Okay, and the emitter is grounded. So the emitter is grounded like so. That's the emitter of an NPN transistor. The base is fed through a constant current source of 10 microamperes. This guy is 10 microamperes, and the collector is connected to a 5-volt DC supply through a 3 kilo ohm resistance. Okay, 3 kilo ohm resistance. I think assuming that the transistor is operating in active mode, find VBE. So this guy is collector, this guy is base. Okay, you're supposed to find VBE and VCE. Okay, all right. Let's see if we can do that. Okay, so what happens is once we have the value of what else is given? 10 microamperes is given. 5 volts power supply is given. Okay, RC is 3 kilo ohms. Okay, once we have that, we should be able to apply. See, here is the small, here is the pi model, the large signal model for BJT that is applied. Okay, the first step is to find the VBE value. Okay, you can find the VBE value. How do you find the VBE value? Well, we know the equation, right? IC is IS exponential VBE over VT, right? So it seems we have just about everything except this guy. Okay, we have IS is given. We have VT, we know VT is 25 millivolts, and we have IC. Do we have the value of IC? Is everybody with me at all?
Yes, I think we have value of IS.
We do have the value of IS, sure enough. That's given to be 10 to the negative 15 or something. Yeah, right there. We have the value for IS, okay? But I'm talking about using this equation, right? IC is this equation. In this equation, my claim is that in order to find VBE, I have just about everything. It doesn't appear that I have IC, but IC can be found out by noticing that it is beta times IB, right? The definition of beta is IC over IB, okay? So IB is given. The value of IB is given to be 10 microamperes.
Okay.
Once we have this value of 10 microamperes, this guy, okay, once we have that, we should be able to calculate the value of IC. Okay, so once we have, and that's what you see here actually, as a matter of fact, IB times beta. So this is in the denominator of the denominator, see? So that's IB times beta. It's simply a rearrangement of this equation here. And that's where this exponential is converted to a logarithm, okay? And then you can see that IC is expressed as IB over times beta. So once we do that, we should have a value for VBE. VBE, remember, is pretty close to 0.7 volts. That's the voltage across the forward bias diode. Okay, so what we have done is to find VBE. So IC is beta times IB. Okay, so that's this voltage, VBE. Once we have VBE, we determine VCE from this guy. So look at this, we have the value of IC, okay? That's beta times IB, and we have the value of RC. RC, remember, that was 3 kilo ohms, okay? So in order to find the voltage at VC, all you have to do is 5 volts minus 3 kilo ohms times IC, if this guy is IC. Okay, so using Ohm's law, we should be able to find the value of VC. Once we have VC, we should be able to find the value of VCE. Okay, let me add a page. Let me copy this. Okay. It's almost so straightforward. It's so straightforward that you can almost do it just by observation. Okay, when this guy is 10 microamperes, I know the current flowing in here is going to be, let me reduce the pigmentation on this. I know this is going to be beta times IB, because this guy is IB, right? IC is this guy. Once I have IC, I should be able to find the value of VC. VC is simply 5 volts, which is the voltage on the top, minus the voltage dropped across 3 kilo ohm resistance. Okay, once you do that, you'll get the value of VC to be some 3 volts, 2 volts. It's 2 volts. Okay, VC is 2 volts. Because VC is 2 volts and V emitter is 0 volts, because it's tied to ground, VCE is also 2 volts. Okay. And then the next, so we found out VBE, and we also found out VCE. So we found out VBE, and we found out VCE. Okay. Now the problem goes on to talk. The problem goes on to say, what value do you have to apply if you were to get rid of this 10 microampere current source? You still want the same amount of current flowing in there. Connect this guy to 5 volts power supply and use RB over here, okay? And then if you still want to maintain a 10 microamperes current, what would be the value of RB or RBB? Okay, and in order to do that, you have to remember that this guy, the voltage at VB, came out to be 0.69 volts. Remember, that was the first solution that we found for VBE. Okay, once we have this guy, you know the voltage on one side of the resistance, you know the voltage on the other side of the resistance, and then the amount of current flowing through that is 10 microamperes. So you should be able to find the value of RBB or RB, which comes out to be 431. Okay, that's the value of the resistance that you need to apply if you wanted to replace this, if you wanted to replace the current source here. Okay, so that's one problem. Let's see if we can do another problem. Let's do another problem. And this time I don't like annotating on the same slide. So let's see if I can write it out in a separate page, okay? The transistors in the circuit, so this is example 6.2, in the circuit 6.14 has a beta of 100, so beta is given to be 100, and exhibits a VBE equals to 0.7 volts at IC equals to 1 milliamperes. Okay, design this circuit design the circuit meaning pick a value for RC and pick a value for RE so that IC, new IC is 2 milliamperes, and also says the collector flows and 5 volts appears across the collector. VC is given to be 5 volts. Okay, so this is the information that is given to us, and we can, like I mentioned in the earlier problem, it's very easy to reasonably easy. Let me not make it sound like it's a trivial problem. It is easy after you do enough practice to do the whole problem by observation on the circuit. Okay. So this is the problem here. Okay. The first step that we want to do is, how do we proceed? Do you have any suggestions on how to proceed?
I would start from the top to the bottom.
You would start from the top to the bottom, meaning?
We're gonna find RC first.
You want to find RC first? Sure. How would you do that?
So we are given the VC and we have 15 volts on the upper node.
So RC equals to
15 minus 5 divided by 2 microamperes.
2 milliamperes, right?
Yes, sorry.
Okay. 2 milliamperes, that's the required current. Okay. This is what you're designing for. Okay. So this gives me an RC value of 5 kilo ohms. Okay. So because I was going to design this to be 2 milliamperes and VC is given to be 5 volts, okay, I can find this guy. I can find IC. Now what? What would I do next?
So VB is given to be 0.7 volt.
VBE is given to be 0.7 volts at IC equals to 1 milliamperes. Okay, it's going to be slightly different, VBE1. VBE is not going to be 0.7 volts at IC equals to 2 milliamperes. It's going to be slightly different, right? So how do you find VBE from this information? Well, what we can do is use this idea here, IC equals to IS exponential VBE over VT. Okay, so that's the idea we have. And what I want to do is to find Okay, find, let's see, IS. So let me call this IC1 corresponds to VB1. IC2 is still IS exponential of VBE2 over VT. Okay, so what I can do is, so in other words, for the value of IC1, I have VBE1 of 0.7. So this is 1 milliamperes IC, and then VBE1 is this guy. So for VBE2, which is here, oops, I wanted to do this, okay. Okay, this guy corresponding to 2 milliamperes, okay. What I would have to do is see if I can massage these two equations, IC2 over IC1. If I do that, I'm going to divide these two, cancel out the unknowns over here. I'm going to be left with an equation that looks like this, okay? That looks like 0.7, which is VB1. So this is VB2, is VT, IC2 over IC1. IC2 is 2 milliamperes. IC1 is 1 milliampere. Okay, so all I have done is simply use this equation, okay, to find the value of IC2, to find the value of VBE2 that gives me a current of IC equals to 2 milliamperes. And if you plug in the numbers, that's going to come out to be 0.717 volts. Okay, so V base to emitter should be 0.717 volts. Okay, questions, please. Questions so far?
What was inside the control log of VB2? I didn't see the argument. Sorry.
Yes, this is IC2 over IC1.
Oh, okay. All right. Thank you.
Okay. Okay, other questions, please.
So Professor, sometimes we approximate VBE to be 0.7 volts, and sometimes we are trying to find that out. So how do we know that when we can approximate it to 0.7 and when do we have to find it and not approximate it?
When we are doing the DC analysis, which is what we are doing in this case, when we are doing the DC analysis, if you have different value of VB and different values for IC, okay, then if you have three of the terms and you're interested in doing the DC analysis, okay, then you can use the exponential relationship to find out the unknown. Sometimes when you're doing the AC analysis, okay, small signal analysis, which I'll talk about shortly, what you typically do is you hold VBE, the IC1, the operating point, constant. And then when you're doing calculating IC2, a small change in IC1, you don't have to calculate VBE2 over there. So for small signal analysis, you can approximate VBE to be 0.7 or the operating condition, one of those. But then when you're doing the DC analysis, the signal swing is so high, okay, that you have to change the IC value. So if I have to put it in a different terms, IC was 1 milliamperes and the new IC is 2 milliamperes. So it's doubled. It increased 100-fold. So that's a large increase in IC. Then you have to recalculate VBE2. But if the increase in VIC is small, then you can ignore the new value. You can say the new value of VBE2 is going to be very close to the value there. Does that make sense?
Yes.
Okay, so when you
all
want to
the
take that into account is when there is a significant change in IC. Okay.
Okay.
Yes. Was there another question?
like a general question. So all small signal analysis is known as AC analysis,
Yes.
right?
Yes. 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 And it's my mistake that I did not clarify this earlier. So I'm going to let me write it out here. This is what I'm going to do. Okay. Let's see. VBE is all DC values. We also call this large signal values. Little v, little b, little e is the AC values. You also call them the small signal values. Okay, and then the equivalent of this, when you apply VBE or the small signal VBE on top of the large signal operating point, we like to represent that using capital V, little ve, which is the overall signal, which represents the DC value plus the small signal that is applied. Okay, so this is the convention that we like to follow. So because we are doing the DC analysis here, okay, I'm using all capital values. So I should really be using capital IC. Okay, cap IC, because this is all DC analysis. Okay. All right, so what we are doing is to find the new value of VBE because the IC has changed significantly, and that's doubling in the value of IC. So I better recalculate the value of VBE2, which comes out to be 0.717. Okay, once I have VBE, what is VBE? VBE is the potential difference between the voltage on the base to the voltage on the emitter. Okay, but because VBE is 0.717, VB is 0, VB minus VE is given to be that guy. I should be able to calculate VE to be negative 0.717 volts, right? So we have a value for this guy. Okay, we have a value for V base to be 0, V emitter is going to be negative 0.717 because that is what sets up a potential difference of 0.717 between them. Once I have this guy, I should be able to calculate the I emitter. Okay, I could have done it differently. I could have simply calculated IE to be IC over alpha. Okay, and if you don't remember that, IE is IC plus IB, right? And IB is IC is beta times IB. Okay, so we can calculate IE to be beta plus 1 times IB. Okay, so we have a value for IB, I believe. If we don't, we can write it in terms of, we can write all of this in terms of IC. So this guy can be expressed as IC by beta. Okay, beta plus 1 by beta times IC is IE. Okay, so I should be able to calculate the, I should be able to calculate the value of IE to be IC by alpha, where alpha is beta by beta plus 1. Okay, we saw that number earlier.
Professor, question, like how do we define beta? Like beta definition.
Beta is we don't have any control over that. That's a parameter that is controlled by the temperature and the underlying physics. So we can't control that.
Okay.
Okay, that'll be given for our problems. Okay, so I'm
And
going to
alpha,
clean this up quite a bit. Yes,
and alpha is the current gain, right?
it's the current gain factor, correct?
Current gain.
Okay, so all of this is, we don't have to get lost because of these formulas. If you have IC and if you have beta or IB, so if you have two of these, dang it, if you have two of these, you can calculate the third. Okay, similarly, IE is IC plus IB. Okay, so all you need is the value of beta and one of these, IB or IC. Once you have one, you can calculate the other. Okay, so once you know both of these, it's easy to calculate IE, and that's exactly what I'm doing here. IE can be calculated from IC and IB. Okay, and then there are the different terms. IC over IB is called beta, and then IB over IC is 1 over beta, and then IE in terms of IC is called by an alpha term. It's simply rearrangement of this equation over here. Okay, IE is IC plus IB. That's all we want to remember. Okay, questions, please. So once we have that, we should be able to find the value of I emitter. Okay, I in the emitter, which comes out to be, so IE was 2.02 milliamperes. Okay, IC is this guy. Okay, IC is 2 milliamperes. Once we have IC, I should be able to calculate IB, which comes out to be 2 milliamperes by beta, which comes out to be 0.2 milliamperes. Okay. Once we have I beta, I should be able to calculate IC, IE. Okay. So that's what I found out. The sum of IB and IC. Okay. Sum of 2 and this, sum of 2 milliamperes and 0.02 milliamperes gives me IE. Okay. Once I have IE, okay, I have IE, this value, and the voltage on the top of the resistance and the bottom of the resistance, I should be able to calculate the value of RE, okay, using Ohm's law. Okay, that's all I will do. RE will come out to be 7.07 kilo ohms. Okay, and that's the problem that we were asked to find. Okay, what's the value of RC? What's the value of RE? Okay, we are simply using the equation that IC is beta times IB. Okay, IC is given. We should be able to calculate IB. Once we have IB, we should be able to calculate IE. Okay, once we have IE, in order to calculate RE, we have to use the VB equation. Okay, does that make sense? Okay. Questions, please. Further questions. Okay, so the general procedure is I have IC, I should be able to, and beta, I should be able to calculate IB. Okay, once I have IC1 and IC2, VBE1, I should be able to calculate VBE2. Okay, I should be able to find that out. Once I have this, and this gives me IE as well. Okay, IC and beta gives me IE as well. Once I have that, I should be able to calculate RE using Ohm's law. Okay, RC was also found using Ohm's law. Okay, that's all there is to this problem. Application of Ohm's law, and then application of this beta term, and then the exponential equation relationship. Okay. All right. So let's look at the other region that we have been ignoring so far. In the last class, in the active region of operation, or in the active region of operation, the large signal model was this guy, right? There was one diode, and this guy was reverse biased. Okay, this diode was reverse biased. Therefore, I did not show it. I showed it as an open circuit. Reverse bias diode is an open circuit. Okay. In the saturation region of operation, both the diodes are open circuited. Okay, or forward biased. Both the diodes are forward biased. Therefore, you see a diode between the base and collector. Okay, this is the collector base junction diode. Okay, collector base junction diode. Corresponding to that, there is an exponential on VBC. Okay, if both the emitter base and base collector junction are forward biased, then BJT operates in saturation region, similar to the triode region of operation for Mosfets. Okay, this is similar to the triode region of operation for Mosfets. Okay, the collector base junction must be forward biased by roughly 0.4 before IC and beta can drop off. So this is called the edge of saturation is at negative is at 0.3 volts. Okay, in other words, if the forward bias voltage between the terminals of these two terminals of this diode is 0.3, we are on the edge of saturation. Okay, if the voltage goes up, then we go into linear region. If the voltage goes down, we go into deep saturation region. Okay, I'll show that to you when we show a 0.2 volts for deep saturation. Okay, edge of saturation is when the voltage across these two terminals is 0.3 volts. Okay, so here we have a voltage drop between the collector and the emitter, okay, to be 0.2. Okay, between the collector and emitter to be 0.2 in deep saturation. Okay, in deep saturation. In the forward active region, we get good gain. In the forward active region, we get pretty good gain and pretty good output resistance. We want both of those. Okay, as you'll see, the intrinsic gain, and this is not something the textbook talks about. Okay, but this is something we want to understand. The intrinsic gain, okay, is a factor of beta times R naught. okay, for BJT. For MOSFET, the gain that you can get is GM R naught, okay, for MOSFET. The intrinsic gain, the maximum gain that you can get is the intrinsic gain. And if you add a resistance in parallel, you'll get a lower gain, okay? And then these gain values are negative, they're inverting in case, we'll see shortly, okay? So the idea is that when you want good gain, you want to be in the active region for BJT, and you want to be in saturation for MOSFET, okay? When you want a constant current. Now, similar to the triode region of MOSFETs, CBJ must be forward biased. Similarly, okay, similarly, in the forward active region, both the beta value and both R naught are really high. When both beta and R naught are high, you get much better intrinsic gain. Okay, so in saturation, so let me write out here using this color. In saturation, if you were to look at the IC as a ratio of IB, then you get beta in saturation, right? Beta in saturation, or the current gain factor in saturation, is really, really small compared to your beta in active region. So beta active, the current gain is much greater than beta saturation, the current gain in saturation. So we typically like to operate in the active region, okay? And beta in saturation is called the forced beta. Okay, let's look at another problem. For problem 6.3, okay, it is required to determine the value of VBB. What's the value of VBB here? Okay, that's this guy. That's the voltage on the resistance at the other end of the top end of this resistance over here. What voltage do you have to apply? VBB, that results in transistor operating in active region, okay, with VCE equals to 5 volts, okay? And then we use edge of saturation, okay? And then of course, forced. So just about everything is the same, except that beta forced equals to 10 in saturation region, which is a bad thing for us, okay? And then in active region, beta is specified to be 50. So the active region current gain is 50 times the forced region current gain, okay? So what you'll see is if you were to find out VBB in the 3 of these cases, if you were to find out VBB in 3 of these cases, VBB in the saturation region, you have to apply a really, really big positive voltage on VBB to get the same amount of current flowing in collector, okay? In other words, I tell you what, okay? If you want IC to be constant, okay? IC to be constant with a voltage of 5 volts. So if you want IC to be constant, you have to increase or decrease IB based on the region of operation, based on beta value, okay? You know IC is beta times IB, okay? In active region, okay, let me write it out here. IC is going to be 50 times IB in active region. That's because the beta is given to be 50, okay? Now, in saturation region, so this is in active region, in saturation region, IC is going to be 10 times IB, because beta forced is given to be 10. Okay, so if you want the same amount of IC collector current, what you would have to do is this IB can be 5 times smaller than this IB. Okay, this IB needs to be much smaller than this IB. Okay, so let's take a look at this problem, and as a result, VBB, this VBB will be much higher for forced value compared to the VBB for the saturation, for the linear region. Okay, so for operation in active mode, VCE is 5 volts, given to be, VCE is given to be 5 volts. Okay, VCE is given to be 5 volts. So this guy is 5. Once we have this to be 5 volts, I should be able to calculate IC. IC is 5 milliamperes, which is VCC minus VCE over RC. Okay, and that's IC value. Okay, now what we want to do is we should be able to calculate IB based on the value of IC. Okay, IC is 5 over 50, beta is 50. It should give me a value of IB to be 0.1 milliamperes. Okay, once we have that, we can find the value of VBB. Okay, that's what we are asked to find out, VBB. What's the value of VBB? Okay, what's the value of VBB? That's the problem that we are after. In order to find VBB, which is this guy, we should be able to, and we know the value for VBE, 0.7. That's what we are going to approximate that to be, 0.7 volts. Okay, so VBB is going to be IB RB, the voltage dropped across this resistance that is going into the BJT. Okay, IB RB plus 0.7 volts. Okay, so I should be able to get a value for VBE, okay, which is this guy, VBB. Okay, so that's the idea. We get a value of VBB of 1.7 volts. Okay, do the exact same thing for VCE. We use a VCE sat of 0.2 volts. Now, what you will find out is VBB is 10.5 volts. Okay, so I don't want to run through the mathematics here, but what you want to notice is this guy. Okay, the observation that you want to make is in saturation region. This is saturation region, so the beta forced is 10. So by using a smaller value of beta forced, you get a VBB value of 10.5 volts that you need to apply. Compare that guy to the result that you got here in the active region. The first problem, you only need to apply VBB of 1.7 volts over there, while in the second problem, or in the third problem, you have to apply a voltage of 10.5 volts on VBB. Okay, this voltage, you have to apply a much bigger voltage over there. Okay, so that's the idea of in different regions of operation, in saturation and linear region of operation, the main knob is beta. Beta is the main knob. Okay. Let's see. And then there is the idea of base width modulation, where you assumed that the current is going to be constant. Okay, the current is going to be constant as a function of VCE. But then as it turns out, that's not quite the case. There is an effect of channel width modulation. Okay, as VCE increases, the CPJ depletion region widens. Okay, I'm going to write this equation here, add a page here. IC, the expression for IC is IS times exponential of VBE over VT, all of that multiplied by 1 plus CE over VA. Does that remind you of something? So this is equation for collector current of BJT.
Like in MOSFETs, we use this type of equation for drain.
Correct, including base width modulation. Okay, including the base width modulation. Let's see, base width modulation. Okay, so I'm going to draw out the BJT transistor over here. Okay, there's the collector, there's the base, there's the emitter, and its dual cousin, the drain, gate, source MOSFET. Okay, MOSFET has a channel length modulation. Okay, and then this guy has so channel length modulation in saturation region and base width modulation in active region for BJTs. Okay, so the underlying current equation is IC is IS exponential of VBE over VT. Okay, now here ID equals to 1/2 mu n C oxide W over L VGS minus V threshold the whole squared. Okay, there is an undeniable similarity between the two. Give me a second to point them out. Okay, the drain current that's flowing in the drain is similar to the collector current IC over here. Okay, so that's this guy IC is similar to the drain current. Okay, now there is this term IS, which is a factor, which is a term that is dependent on the underlying physics. Okay, there are a lot of terms that determine IS. Okay, including the area of the BJT junction. Okay, including the dopant concentration, intrinsic dopant concentration right here. See, there's area. There is intrinsic dopant concentration. Okay, there's the width, so on and so forth. There's a bunch of parameters, the physics, the underlying physics that determines IS. Similarly, when I compare that to its cousin BJT over here, so that physics is always all represented using this guy. Okay, now there is a relationship, there is an exponential relationship. There's an exponential relationship in BJTs, while there is a near square law dependence in MOSFETs. Okay, similarly, the input terminal, let's see, I'm out of colors here. Okay, the input terminal VBE voltage corresponds to VGS over here. If you think about it, V base to emitter, the voltage here to this guy is similar to gate to source, this guy to this guy. Okay, so VGS, that's the input voltage earlier, and then VB is right here, and then of course there is VT and V threshold voltage. There is that point, but the idea that you want to remember is the way you incorporate the channel, the base width modulation here is to include all of this, okay, include all of this and simply multiply that by the early voltage, okay, into 1 plus lambda VCE, okay, 1 plus lambda. So 1 over BA is lambda, all right, the channel length modulation parameter in BJT, in Mosfets, the base width modulation parameter here, okay. And if you remember the MOSFET equation that I gave you some time ago, okay, so this guy is for BJTs. For MOSFET, how do you incorporate the channel length modulation? You simply multiply that by 1 plus lambda VDS for MOSFETs. So you can see that there is an undeniable relationship, similarity, okay? And then while the current in one is an exponential function of the input voltage, in the other device, in the MOSFET, the current is a square law dependence, is quadratic, has quadratic dependence on VGS. Okay, so both of them, one has a body width modulation and the other has a channel length modulation. And as it turns out, you can play around with the value of W over L in MOSFETs, but you can't do that with BJTs. Okay, we cannot, to the most part, we cannot play around with the aspect ratio of BJTs as much as you can play around. As a matter of fact, for MOSFETs, one of the design parameters is the aspect ratio. Okay, so models with base width modulation. So let me highlight this part. The base width modulation, 1 plus lambda VCE, that is incorporated here. Okay, 1 plus lambda VCE, where lambda is 1 over VA. Okay, base width modulation term. If you were to incorporate that into your model, okay, earlier we had a model that has a diode and a current source. Now what you do is this base width modulation corresponds to a resistance R0. Okay, when you did your lab, okay, if you were using the CD 4007 and doing this simulation, okay, when you're doing the simulation and you were sweeping VDS for your MOSFETs, VDS for MOSFET CD 4007, okay, as a function of ID. Okay, you should have seen something like that. Okay, there is a slope to the ID VDS curve. This slope is inverse slope of this. If you take the inverse slope of this, okay, that gives you R0, okay, or delta ID over delta VDS will give you GDS, okay, but if you do the inverse slope of it, delta VDS over delta ID will give you R0. Okay, the slope of the IDVDS curves will give you a resistance that you have to incorporate that resistance into your or not. Remember, this slope, all of this slope is coming from the fact that there's a channel length modulation. Okay, similarly, that's the exact same thing here as well. The slope to these curves is coming from the base width modulation, as opposed to these being straight lines. Okay, as opposed to these being straight lines, there is a base width modulation effect that makes them curved, slant lines. Okay, and then when they're slant, and you extrapolate them, they meet at a point negative VA. The slope of that will give you. So the inverse slope, the point being, the inverse slope of this guy will give you what is known as the R naught. Okay, so that's an addition that you do, an add-on, an enhancement to your BJT model to include the output resistance. Questions? Okay, what was the value for lambda in BJT? What was the value for lambda in BJTs? You remember, in terms of ID, I must have mentioned something in terms of ID or R naught in terms of lambda and ID. R naught is 1 over lambda ID in Mosfets. Okay. Similarly, in BJTs, you can find R naught is 1 over lambda IC. Okay, that's exactly what you'll find here. Once you have VA, you should be able to calculate lambda, or you should be able to calculate 1 over lambda IC. Okay, so once you're comfortable with the one scheme, one type of device, MOSFET, that should, all of that should translate into BJT and vice versa. Okay. Now let's look at the higher order effects, the effects of temperature. These are pretty similar to the diode higher order effects. So I might as well go back to the diode higher order effects. Okay, I might as well go to the diode. Okay, and look at the higher order effects. Is it this guy, or did we look at diode in semiconductors? Okay, built-in potential. Okay, so let's see the higher order effects. Where did the higher order effects? If I can go back to the diode higher order effects, the effects of temperature.
I think it was in chapter 5.
Right here. Okay. The diode has a temperature dependence. Okay. The bias voltage across a diode, which is carrying a constant current, drops as the temperature goes up. Okay. Or in other words, by increasing the temperature at a higher temperature, I need really small voltage. Okay, this voltage is smaller compared to V1, V2. So at higher temperature, okay, shown in purple, highlighted in purple, I need a small voltage to conduct the same amount of current, which could lead to a thermal runoff. Okay, so that's exactly the idea here. Okay, so if I go back to BJTs, at higher temperature, okay, T1 is the highest. Remember, at higher temperature, I need a much lower voltage to conduct the same amount of current. Okay, so this can cause a thermal runaway. what happens is when the temperature increases, the current goes up. And as the current goes up, it increases the temperature further. And then there is a feedback, okay, that that eliminates that leads to your BJT frying. Okay, so what we typically like to do is to bias the current, bias the BJT at a constant temperature. Okay, so here is a plot of VBE versus. The idea is that as we increase the temperature, the same amount of current needs much lower voltage. Okay, I need much lower voltage to have the same amount of current. That's the idea of temperature effect. Okay, and then the exact same higher order effects as in PN junction diodes. There is reverse bias leakage currents. Okay, as a matter of fact, we looked at reverse bias leakage current in Mosfets as well. The source bulk diode and the drain body or drain bulk diodes. You always want to reverse bias them, but there's a small reverse bias current flowing through that. And in addition to that, if you increase the reverse bias voltage significantly, there's going to be a reverse bias breakdown. Okay, so this is something that we discussed. When it comes to biasing BJTs, okay, here is a summary of the different regions of operation. And when we are looking at BJT or MOSFET as an amplifier, we like to operate in the active region. So there is a 0.7 voltage drop between the base and emitter. Okay, and then there is a beta times IB multiplication factor. Okay, there's a beta times IB multiplication factor between the base current to the from the base current to the collector current. Okay, that guy is multiplied by beta. That's the DC bias models. Okay. Now let's see. Consider the circuit here, which is redrawn to remind the reader of. We will assume that beta is specified to be. We wish to analyze this circuit to determine all node voltages and branch currents. Okay. So let's do a quick comparison between this guy. Okay, I'm going to add a page here. And I'm not going to go dwell in the problem a whole lot. It's a mathematical calculation, but I'm still going to provide you some intuition. As a comparison between this problem, this is example 6.4. Okay, let's compare this guy to the earlier problem that we did. Okay, this guy over here. Okay, let's copy it over here. Okay, and I'm going to okay, this is problem number. I don't remember what problem it was. 6.3. Okay, this is example 6.3. Okay. The problem was still the same. You're given some voltages. Okay, you're given this guy. You're asked to find this guy here. Okay, what's the value of IC? What's the value of VC? What's the value of VB? So on and so forth. Okay, VBE, so on and so forth. You were tasked with finding the exact same thing. Analysis problem again. This is all an analysis problem. But what big difference do you see between 6.3 and 6.4? Do you see a difference between the two?
.3 has a resistor on
6.3 has a resistance on the VBB. That's fine. Let's say that's mainly to That's mainly to make sure that we get a current that's very small. Okay. What else? That is correct. That's one observation. There's no resistance over here. Okay. There's also another resistance in the emitter right here. That is of interest to me. Okay. And I'm going to mention in an intuitive manner. You can refer to Dr. Headley's lecture for the problem solution itself. I want to talk about something that is a little less, that's ineffable. You cannot readily look at these problems and find out what's going on, but there is an invisible feedback here, because of which it is inherently more stable. What do I mean by that? Okay, look at this problem. Let's say I'm making IB to be constant. Okay, let's say IB is constant and beta is varying all over the place. Okay, beta is not constant, it varies with temperatures and a lot of other variables. Let's say beta is varying all over the place. What do you think happens to IC? What happens to IC as a result?
Changing.
It's increasing, right? Because IC is beta times IB, even though you're holding the input current constant, simply because of the variation of IB and because of a wild variation of IB, your IC is all over the place. It's not constant. You don't get a constant operating point. Your gain is moving all over the place. It's not a good place to be in, right? Your VC is varying as a result, so on and so forth, right? What do you think is happening in this case? What do you think is happening on the right-hand side that makes it more stable and less immune to changes in beta? Okay, there is a resistance in the emitter here. This is a very subtle concept, and that's a very interesting notion as well. What happens is, let's say you hold IB to be constant. Okay, let's say you're biasing this guy to be constant. And then let's say your beta is increasing. Okay, when your beta is increasing, what should happen to IC? When your IB is constant and beta is increasing, what happens to IC?
Increasing.
Increases.
It's increasing. It should increase, right? So let's say IC is trying to increase. Okay, then earlier when IC increased, there was no way for me to restrict or keep it from increasing. But here, because of the resistance down below, think about what happens. Okay, when IC increases, okay, the amount of current flowing IC here increases. What do you think happens to VE? That's the voltage on this guy, right? If there's a large current flowing through the resistance here, the VE is going to be large. If there's a small current flowing in here, there's going to be a small value in VE. So as IC increases, would you agree with me that VE increases? Yes or no? Because IC times I or IE times RE increases, right?
Is V. Yeah, so
Which is the same as VE, right?
mhm,
So as IC increases, VE increases. When
yes.
VE increases, what do you think happens to VBE, which is VB minus VE? Okay,
So it will decrease.
it will decrease. Okay, now what happens? Something magical happened now. Okay, if you think about it, okay, by increasing, okay, let's see, by increasing IC, I increased IE, and by increasing IE, I increased VE, and I decreased VBE. Okay, when you decrease VBE, what do you think happens to IC? Go back to the equation. What is the equation for IC? Okay, the equation for IC is that IC is exponential of VBE. So when VBE decreases, IC should decrease, right? So
Decrease.
what is, it should decrease, right? So as a result, what happened is IC as a result will come down, okay? So just by adding a resistance here in the emitter, okay, any increase in IC because of a wild change in beta varies all over the place. That's the big crappy variable, right? Because of an increase in beta, IC increases and it kickstarts a chain of events that eventually reduce IC. So in other words, there is a built-in mechanism to reduce the overall volatility of IC. Okay, so there is some kind of feedback mechanism through this resistance RF, a very subtle, a very hidden, invisible feedback. Oops, I said invisible feedback, right? There's an invisible feedback that is being provided by this resistance RE, which discourages any sudden changes in IC. And as a result, this is a better, the one on the right is a better DC bias solution. Does that make sense? Questions, please. Okay, the one on the right, the solution on the right, the DC bias solution on the right has a built-in stabilization mechanism because of which any large changes in beta do not necessarily reflect into changes in IC. Okay, that's a point. But then I welcome you to go through this problem. Okay, it's just a matter of applying these different steps. Okay, this is supposed to be, one of these is supposed to be at, this is at 4 volts, right? When this is at 4 volts and you know for a fact that this is 0.7 volts, then you should be able to calculate VE over here. Okay, you know VE is going to be 0.7 volts below VB. Okay, that's a diode. So once you have this voltage here, the next step is in finding out the current. Once you have this current, okay, you should be able to calculate, this guy. Once you have IE, you should be able to calculate IC. Okay, IC is IE is IC plus IB, and then you can use the formula that relates IE and IC. Okay, IE is simply alpha times IC. Okay, or the other way around. IC is alpha times IE. Okay, so when alpha is 0.99, which is beta by beta plus 1. Okay, so the idea is once you have IC, like I mentioned, if you have IE and beta, you can calculate IC and IB. If you have beta and one other term, you can calculate the other currents. That's all there is to it. So that's the third step. Once you calculate that IC, you should be able to calculate the voltage over here, okay, which is simply the Ohm's law, application of Ohm's law. Also, you can calculate this guy, okay, IB is simply IE minus IC. Okay, so all there is if you have beta and one of the three currents, doesn't matter which one. If you're given IB, you simply multiply that value to get IC and add the two to get IE. So you have beta and one more current, it's easy to calculate the rest. Okay, so that's the idea. And you calculate and then you find out the node voltages and node currents. Okay, that's solving the problem. But then I wanted to give you more than just being able to calculate that problem. And then of course, what we did here is to solve this problem just by looking at the figure rather than having to go through very elaborate equations and calculations. Okay, so our calculation, the first step, the first solution of finding VE is predicated on the observation that VBE is 0.7 volts. So once I know VB, I should know the value of VE. Once I know VE, the rest of the problem unfolds in a really systematic and very predictable, easy path. Okay, the key observation is that this guy is 0.7 volts because it's a forward bias diode. Okay, so step number one is forward bias diode. Step number two is Ohm's law. Step number three is this guy, alpha beta relationship between alpha, IB and IC. So this is application of alpha. Step number four is again Ohm's law. Step number five is the usage of beta. Okay, or the idea that IB is IE minus IC. Okay, so those are the steps. I welcome you to plug the numbers in and see how you can solve that. Okay, so what we have done is we have done the circuit analysis on the circuit diagram without actually going through lengthy calculations. That's the idea. So let's do one more problem. We want to analyze the circuit and determine the voltages at all nodes. Okay, what we want to do is to be able to analyze this circuit. Okay, so the first step that we want to do, this is a PNP diode, right? This is a PNP diode. So this is a PNP transistor. So I know for a fact that this diode needs to be forward biased. So the voltage here should be 0.7 volts above the base. Okay, so going off of that, so forward bias diode gives me a value of 0.7 volts for the V emitter. So here is the emitter, right? This is the base, this is the collector. Once I have that, I apply Ohm's law. Okay, I apply Ohm's law to find out IC. Okay, once I have IC, I should be able to calculate IC or IC times alpha should give me IE. Okay, alpha is nothing but beta by beta plus 1. Okay, the value of beta should be given somewhere. Okay, the value of beta or alpha, one of those should be given in here. Okay, Now, once we do that, once we, let's see, since no beta has been given, we assume beta is to be 100. So that's a little assumption that we do. So step 3 is the application of this formula. IC times alpha is IE. And then step 4 is once you have IE, that's the current flowing through this, we should be able to calculate VC using Ohm's law. Okay, once you calculate this guy, VC, you should also be able to calculate IE or IB, which is simply IC over beta. Okay, IC over beta. And that's the idea. Okay, the collector current over beta, which is point, if you think about it, it's 4.6 milliamperes is IC. Divide that by 100, you get roughly 0.05 milliamperes. IB is IC over beta. Okay, so those are the steps that we are using here to one by one. Okay, questions, please. So these will mostly likely be the steps that you will do. Okay, for many biasing problems. The first step will be identifying a forward bias diode in active region and finding its value, approximating its value to be 0.7. Then your step would be to do the Ohm's law. Okay. Second step would be Ohm's law to find out IE. Once you have IE, this is IE, right? Once you have IE, you should be able to calculate IC and IB. And then, of course, once you have IC, you should be able to calculate VC. Okay, so that's Ohm application, a couple of times Ohm's law used, and then one application of forward diode approximation, and then a couple of applications of the beta alpha IE IB IC relationship. Questions, please. Okay. All right, I want to stop here and let me take stock at where we are and where we need to be. If only I can find the syllabus. Okay, syllabus, today is the 23rd, right? So let's say 23rd, I'm supposed to be talking about bipolar junction transistors. Good. Okay, so we are on pace to finishing bipolar junction transistors. Hopefully, let's see, hopefully, how many pages do I have more? 10, a few more pages. So I got a little careful this time around. The last time when I was talking about Mosfets, I got stuck doing the problems over and over, repeating myself, trying to make sure you clearly see every little detail in the chapter. So much so to the point that I could not finish all the slides, okay, some of the concepts. So this time around, I'm spending a little bit less time on the BJTs in terms of the problems. I'm only giving you the big picture and the big steps that you want to follow without actually plugging in the numbers. That way, we have some time reserved to go over the all the slides. And in addition, hopefully, given that we are a little ahead of schedule, what I want to be able to do is to give you a leg up, a head start on the next chapter, which will be, let's see, the amplifiers, okay? Amplifiers, single transistor amplifiers using BJTs and Mosfets, okay? So that'd be common emitter and common source amplifier. I don't know if we are going to look at common source amplifier using Mosfets, but it's really very similar to common emitter in BJTs. All right, questions, please.
I have a question, Professor, about the lab schedule.
Okay.
So in
Let's see
Moodle,
if I can go back to, yes.
In Moodle website, it says that Lab 8 is, it was actually extra credit for students in spring, and they were not supposed to do that. Like if they do that, it will be extra credit. So is it the
Yeah.
same for us? Or?
Yeah, that's something I wanted to make as an optional exercise towards the end. So if you, let me say that one more time, until lab 6, yesterday was the deadline to submit all the labs until lab 6, right? So if you want to spend some time on lab 7 and get started with lab 8, we'll make this extra credit, okay?
Okay, thank you.
We'll make this extra credit just so you, I tell you what, let me do this.